Thank you for giving me the opportunity to speak in this seminar. Right. So let me begin by giving somewhat of a short summary of the idea of how to count coherent sheaves in Calabi-Yau fourfolds. So this has been a rather recent development, with solutions given to these questions independently by Borisov-Joyce and Cao-Leung, where this was given for just some cases, and recently a paper of Owen Thomas expressing it in a more algebraic setting, while Borisov-Joyce used derived algebraic geometry and derived differential geometry. So the idea is that in Calabi-Yau fourfolds, unlike in Calabi-Yau 3 or Calabi-Yau 2 case, we now have three terms that we need to take care of, which is the x1, x2, and x3 group. And using Serre duality, we have duality on the first and the third group, and the second x group has a bilinear form on it, a non-degenerate bilinear form. Now, the slogan for constructing these virtual fundamental classes, which are used to count these coherent sheaves, is to take half of everything. So once you take x1, you have covered x3 by the duality. So let me just say an equivalent way of looking at this. You're either taking a real subspace of this direct sum x1 plus x3, which is invariant under the Serre duality isomorphism, and the other way of looking at it is that you're taking the isotropic subspace x1, and this isotropic subspace is isomorphic to your real subspace that you take, and the natural orientations on this real subspace that you have, because it is a complex space, are compatible with the fact that you're choosing the first X group as your isotropic subspace. Now, what's left over is choosing an isotropic subspace of the second X group, which is equivalent to choosing some orientation on the real part of it, and somehow fitting these choices continuously. So to formulate it in a more mathematical way, let me just for now assume that our x2 is a vector, just any complex vector space with a duality on it, and VR is a real subspace of it. Then choosing an orientation on VR is the same as choosing orientation of its determinant on a real determinant, meaning the highest external power, which corresponds really to choosing an isomorphism of it to the real line. In other words, after just computing kind of in this in canonical basis, this is equivalent to saying that you choose an isomorphism from the complex determinant of the complex vector space V into C, such that if you take the second power of this isomorphism, if you take identity tensor, what I meant to say is if you take the second power of this isomorphism, then this will be equal to using identity tensor, the duality, composed with the natural canonical isomorphism here. So the definition that this allows is the following. If you have a complex line bundle over any kind of space, stack, derived stack, when you have a duality on it given by mu, then one can define a square root Z2 bundle associated with mu, which is simply the Z2 bundle given by the sheave where the sections of it are exactly these trivialization of the line bundle which square to the adjoint of mu, which is exactly what I wrote down here. So why is this kind of, how does it come into constructing these virtual fundamental classes? I will use here kind of the more recent algebraic approach, because that is the one that is more applicable to the non-compact setting because of localization that it brings with it. So if you have X a quasi-projective Calabi-Yau fourfold, now this, what I mean by quasi-projective Calabi-Yau fourfold will vary in this talk. So right now, when I talk about virtual fundamental classes, I will be mostly assuming that I have the condition that the first, second, and third homology of the structure sheaf vanish, or equivalently that it is that we have holonomy SU4. Then in this setting, if you have a quasi-projective moduli scheme of stable compactly supported sheaves, Hilbert schemes of proper subschemes, or stable pairs meaning maps from the structure sheaf to some compactly supported sheaf satisfying some stability condition, then we have an abstraction theory on this, which is a three-term complex, the truncated complex of the R-hom complex of universal complex, with the corresponding Atiyah map into the cotangent bundle on M. And this is indeed an abstraction theory, but it is not perfect because it sits in 3 degrees, and you can find a quasi-isomorphic. So this is something that O and Thomas prove, that there exists such a quasi-isomorphic 3-term complex where T and T star are, I mean, this is just the dual of T, and you have duality on E, which corresponds to having this form on E, turning it into an O and C bundle. So in particular, once you, the Serre duality on this E term, the Serre duality on this E complex transitions to this natural duality on this 3-term complex. And the whole point is that one needs to show that this ONC structure on E, on this vector bundle E, reduces to a SONC structure, which corresponds exactly to existence of orientations in the sense that I wrote down. That is trivialization of this bundle bundle OM associated with this isomorphism on E, which comes from Serre duality. So the theorem, kind of a baby version of it, that I prove, is that if M is a quasi-projective moduli scheme of stable compactly supported sheaves, Hilbert schemes of proper subschemes or stable pairs on quasi-projective Calabi-Yau fourfold. So now in this theorem, quasi-projective Calabi-Yau fourfold means really just that I have a trivial algebraic section, that I have an algebraic section which is nowhere zero of my canonical bundle. Well, in this case, in this setting, the moduli, the orientation bundle is trivializable. So using this, one can then construct virtual fundamental classes using some isotropic cone construction of O-Thomas and this square root localization, which comes from isotropic co-section localization, which I will not really talk about because it's not related to orientation anymore. And the example of that, to kind of have an understanding of what's happening and how the orientations really come in explicitly into the construction and affect the virtual fundamental class, is if you have a smooth moduli space and you have the abstraction bundle, so the abstraction bundle here is a vector bundle now, then the virtual fundamental class will be given by the Euler class of the real subbundle, which always exists by reducing an oriented it comes from reducing an SONC bundle to an SONR bundle. And this orientation is exactly corresponds to a plus-minus sign, which you would be choosing because of choosing an orientation when you take the Euler class of a real bundle. Well, equivalently, one can also take the Euler class of an isotropic subbundle if it exists. So if X is not compact, these virtual fundamental classes are generally not defined. However, this virtual structure sheaf can always be defined. And if M, just for some reason, in very few cases this happens, if M can be compact, in fact, then you will also have virtual fundamental class. But outside of these cases, you will usually need to use localization formula to define your virtual fundamental classes. So the localization in this setting is very similar to Calabi-Yau 3. It's just that you work with this 3-term complex rather than a 2-term one for abstraction theory. So if, well, this is because I have 2 different t's. So here T is a torus acting on X, preserving the volume form such that then the action lifts to an action on the moduli space, and we have the fixed point set in M. Then the abstraction theory, this 3-term complex of vector bundles, splits into the fixed part and the normal part. And under Serre duality, the positive weights of the normal part can be identified with negative ones. So this depends on on the choice of order that you make on the weights. This is easy if you have just one-dimensional torus, because you essentially just have 2 choices. But if you have higher dimensional tori, you kind of have to choose a basis inside of your C star to some power. And these are paired with negative ones, and this gives you then a natural orientation of the virtual normal bundle. So one can use then the orientations in the non-compact setting to do 2 things. In case that your fixed abstraction theory is non-trivial, then using this this natural orientation on the virtual normal bundle, one can induce an orientation from a global orientation on this fixed part of the abstraction theory. And in the other case, when the fixed part is trivial, which is, for example, when you work with toric Calabi-Yaus and you're looking at Hilbert schemes or ideal sheaves, then the virtual normal bundle is equal to the restriction of the abstraction theory to the points, and one should use the global orientation restricted to these points to determine what the orientations of the virtual normal bundle are. So how does this come into the localization formula is written here. So if we have the virtual fundamental class, then first one needs to have orientation on this fixed point locus for the corresponding abstraction theory. And if this is trivial, then one needs orientation on this on the normal bundle or the virtual normal bundle. So because one wants to take a square root and the choice of square root is governed by the orientation. So this approach to computing invariants is used by many authors now, even before it was properly developed by Thomas. So let me just give some names: Cao, Kuhl, Maulik, Munavari, Nekrasov, and Toda. So with kind of the motivation for the work over, I would like to talk about the actual setup and the grown-up formulation of the theorem. So let me start with maybe a language not many are used to, and that is one of derived stack, or higher stacks. But I will not. One shouldn't really think too much about this and just think of these as some generalization of stacks or schemes. So in Toen and Vaquier defined this functor which assigned to DG categories higher stacks, and we use this to assign to a smooth quasi-projective X this moduli scheme, moduli higher stack of perfect complexes, where LP is the DG category of perfect complexes. But because if you are in a non-compact setting, you only have to look at things which are called right proper object, meaning that they're our home complexes have finite dimensions. Then this picks out that, this tells you that this stack only classifies compactly supported perfect complexes, and it forgets everything else. And that is exactly what we want. So now we have the perfect cotangent complex on our stack MX, and which at the C point is given by the shifted X complex, shifted and dualized. And Brav and Dickerhoff prove that the derived stack corresponding to this higher stack is -2 shifted symplectic, which kind of is an extra structure on top of this Serre duality, which is the duality on the cotangent bundle. And and using this duality, one then gets an isomorphism on these canonical bundles, which are determinant line bundles of LMX, and one gets this orientation bundle on the moduli stack of perfect complexes or compactly supported perfect complexes, which is the orientation bundle which we want to prove to be trivial. So the ambitious approach, which may eventually at some point be figured out by someone how to make this work, but I didn't manage to do that, is to assign to each perfect complex something called pseudo-differential operator, which is compactly supported. So this is the idea that instead of just differential operator, you restrict to this more complicated structure, which you can define what it means to have a compact support of. And under this mapping, then the determinant of the R-home complex should correspond to the determinant of this pseudo-differential operator, which is really just the determinant of kernel tensored with the dual of the determinant of a co-kernel. And Serre duality on the R-home complex would correspond to real structures, meaning that you have an underlying real pseudo-differential operator of your of psi. And then the orientations on the left side would really just be orientations on the right side of the real determinant lines. But like I said, this is not this is just for now. It is a good idea to keep in mind when you're trying to work with these things, that this kind of is the goal, but this is not exactly the way that it worked out. So let me say how I how I worked around this. So I used compactifications to do that. where already results are known, and in which, because in the non-compact setting it gets rather technical because it goes back to some Ulysses results which just don't exist for the non-compact setting. So okay, so we have this this topological realization functor defined by Blanc from higher stacks into topological spaces, and for X, a Hausdorff topological space, one can define this space of compactly supported K-theory by taking a one-point compactification and having this relative mapping space. Now, one should think of Cx, of this topological space, as the differential geometric counterpart of the topological realization of this higher stack of perfect complexes. And we will see that there is a natural map from one to another, which is, in some sense, should be thought of as kind of a forgetful map. And now this motivates the idea that the K-theory, the compactly supported K-theory, is generated by classes of three terms, where you have two vector bundles, which are identified at infinity by some isomorphism. So taking this into account, I should try to mimic this on the algebraic geometric side. So the one-point compactification in this case is replaced by a smooth projective compactification by a strict normal crossing divisor. And if we use this notation for any projective scheme Y, and Y is the mapping stack, kind of classifying all perfect complexes on Y, if Y is smooth and compact, then this is equivalent to this stack of Toen and Vauquier that I had on the last slide. So with this notation, this identification at infinity becomes we just say that we work with we have this map, this restriction map from mx bar into MD being the stack of perfect complexes on the divisor, and we say that we look at pairs which are up to quasi-isomorphism identified at infinity. So we take this product stack. So let me just set some notation that I will use. XL is really just the complex of mx, which is given at each point by the Arhelm complex when restricted to each perfect complex E dot. And then we have, it's not the Arhelm, it's twisted by some coherent sheaf L, which need not be compactly supported. We have then the duality, which is just the Serre duality again on it. And if we define lambda L to be the determinant of this complex, and we again have some sort of duality on these line bundles, but this time we get this extra twist because we don't assume that X is Calabi-Yau because we compactified, and we have this L dual of it. So there is some special case in which one doesn't need to do this identification of perfect complexes at infinity, in which one gets orientability in an easier way. So let me just discuss that before I move on to the general one. If X is a smooth projective variety, and we have our canonical divisor, then we can ask for its square roots of this, half of the divisor, which are called theta characteristics. And after making such a choice of a theta characteristic, because there are multiple ones, we say that X is spin. And if we replace L here with theta, then you can see that this isomorphism really becomes a duality on line bundles. So in this case, one still virtual really means and one has the duality and the associated Z2 bundle, and it's possible to show that this one is trivializable. And because all our compactly supported complexes sit inside of this bigger stack of all perfect complexes inside of a spin compactification, we get that in some cases we can prove orientability this way. So for example, C4 can be shown to be orientable by embedding into P1 cross P3. As we see already, quite is not very natural because you need to choose directions to do this, to do such a compactification and get such a orientation. And then one also has the example when one takes the total bundle, total space of a bundle, such that the determinant of the bundle is a canonical bundle and the dimensions add up to 4. And in case that the rank of the vector bundle is odd, then this projectivization of it is spin. Another case is when you have two line bundles over a surface, you get a spin compactification in this way, but this doesn't work if you just have a bundle 2 which doesn't split, or just a general toric Calabi-Yau fourfold case, which seems to be the interesting one. The issue with this approach is also, like I said, is not very natural. Would be hard. I think it probably wouldn't be possible to say that the orientations that one gets in this way would, I mean, I'm quite certain that the resulting orientations would depend on a choice of a spin compactification. So the general approach uses a similar thing, but now with this general compactification. And we have this inclusion of our moduli stack of compactly supported perfect complexes on X into this product stack by mapping into the first component and having 0 in the second one. Now, one can construct a Z2 bundle on this bigger stack by the following proposition. So for a choice of extension data, which I will explain in the process, there exists a natural isomorphism var theta bowtie, or theta bowtie, from this tensor line bundle to its dual, such that its associated square root Z2 bundle comes with a natural isomorphism of its pullback to the orientation bundle that we care about. So how do we construct it? For this point inside of this bigger stack, I will use the notation determinant of EF so that it fits into the slide, not writing our home. So we have then the isomorphism induced by Serre duality, where I just take determinant of E and determinant star of FF, and I get the extra kx bar on the right side. Now one can express kx bar as a sum of these divisors, of smooth irreducible divisors at infinity, which add up, which lie in the union. Well, their union is this strictly normal crossing divisor at infinity. And for each line bundle L, one then has such a this natural, the usual algebraic geometric short exact sequence, which if you apply all of these derived operations, which give you a next group of, which give you this R-home complex of E and F to this, one gets a distinguished triangle, and applying the determinant, which is multiplicative with respect to distinguished triangles, one gets this isomorphism, which removes a contribution of a divisor on this right in the second term, and applying this multiple times, so one removes the entire canonical bundle, one gets exactly this isomorphism, which is the duality isomorphism that I wrote down in the beginning, in the proposition, and one associates this Z2 bundle to this isomorphism. Now, the extension data is the collection, so if I go back, the collection of these sections SI that I wrote here, and the order in which you do this removal of a divisor. And the condition for it to pull back to the orientation that you care about is that the product of these sections is a meromorphic extension of the Calabi-Yau volume form on the quasi-projective Calabi-Yau that you started with. So now we reduced our problem to proving orientability of this Z2 bundle on a bigger stack, which is in the compact setting and therefore more approachable. Oops, I need to go in the right direction. So the main theorem that you can find, so that I prove, so firstly I have this map from this product stack into the product of this K-theoretic, well, this fiber product of the K-theoretic spaces, which really corresponds to kind of K-theories classes identified at the divisor at infinity. And the theorem then says that for any choice of such smooth projective compactification by a strictly normal crossing divisor, and any choice of extension data, the Z2 bundle that we constructed is trivializable. And we can say more, and this is the important part, there exists a natural trivializable Z2 bundle on this K-theoretic space such that its pullback is naturally isomorphic to the Z2 bundle that we constructed here. So immediate, oops, I keep going in the wrong direction in my slides, but of this theorem is everything that we wanted, well, almost everything. So if we compose the map from this compactly supported perfect complexes in X into the product stack and then with the map into the K-theory, then this gives us our map from MX into this space, which corresponds exactly to the space classifying compactly supported K-theory. This is these pointed maps. And the theorem that you get from the previous one is then that for any quasi-projective Calabi-Yau fourfold, the Z2 bundle that we had the orientation Z2 bundle is trivializable. In particular, or our problems orientations on, but we also are able to express it up to a canonical isomorphism in terms of pullbacks. In terms of pullbacks of orientations which live on this compactly supported K-theory space, which is just the restriction of the Z2 bundle that was in the previous theorem. And it can be shown that the Z2 bundle does not depend on the choice of orientation, and with some arguments which I wrote down, but I didn't really want to prove at that point anymore, it should be possible to show that this isomorphism is independent of all the choices that one makes in the previous theorem. Oops. Now, a similar story can be done also for Hilbert scheme, but in this case, you would be extending by structure sheaf at infinity. So let me just say it quickly. You map instead your perfect complex corresponding to Hilbert scheme over stable pair to its extension by a structure sheaf and a structure sheaf in the second copy of MX bar. And then under this map, the orientation that you have on this moduli scheme is a pullback. Well, if you enrich it to a stack and then you map it to this more complicated stack, then it is a pullback of this orientation that we constructed with respect to the extension data. So again, this theorem expresses not only that you have trivializability, but you can express, again, the orientation in terms of some differential geometric orientation. So I told you kind of that we get orientability and we express it in terms of differential geometric orientation, but I haven't explained what this differential geometric orientation is. So before I do that, and kind of as a preparation for it, I will talk a bit about this notion of Z2 graded H-principal Z2 bundles, which is quite a mouthful. But essentially what we have is that all our spaces have an addition map on them, which turns them into something called admissible H spaces, but even more so, they are gamma spaces or infinity spaces, which are group-like. This are, well, the H space story means that they are monoids inside of the homotopy category, and the fact that they are group-like just means that these monoids have an inversion map. So now Cao-Gross and Joyce define this weak and strong H-principal Z2 bundles, which tell you that if you have such a, well, the definition is that if you have such an H space, then a weak H-principal Z2 bundle comes with some isomorphism which corresponds to the fact that it behaves well with respect to the sum on this H space. And the strong H-principal Z2 bundle is a weak H-principal Z2 bundle together with a specific isomorphism Q, or where this capital Q needs to be trivializable on top of it. And this isomorphism Q needs to satisfy some associativity condition, which is written down here. Now, I add this extra definition of it, which is the Z2 gradedness, which is supposed to keep track of the signs in this more complicated setting where you have a product stack and you kind of interchange orders. And so if you have a Z2 bundle, then it's Z2 graded if it comes with a map, degree of O, from the space on which it lives into Z2. The point of this map is that if you have such two Z2 bundles, which are Z2 graded, then their tensor product, if you interchange the order in the tensor product, you obviously have an isomorphism, but the natural isomorphism that you get, it actually needs to differ by a sign -1, this should say degree of O1 times degree of O2, and from the naive one. So the naive one would just be really interchanging, and here you need to multiply in addition by this sign. So a Z2 graded H-principal Z2 bundle combines the above two definitions. And in this case, if you have a strong H-principal Z2 bundle OP, then you can associate to it O star P star its dual, which usually when you associate a dual to a Z2 bundle, nothing changes. But in this case, obviously the Z2 bundle itself is unchanged, but the this P star has these extra signs in them which one needs to keep track of. And isomorphisms of these Z2 graded Z2 bundles, which are also H-principal, need to preserve this grading. So examples of these are our orientation bundle on MX, which is well behaved with respect to the addition of compactly supported perfect complexes by having this natural isomorphism, and also a slightly more complicated but still true one has also an isomorphism on the setting where one takes our theta bow tie orientation on this product stack of compactification. This makes them into weak H-principal Z2 bundle, which in addition satisfy this associativity condition on this page. which makes sense because, like I said, these spaces are in fact E-infinity spaces, so this is well behaved. Now, on the differential geometric side, Joyce, Tanaka, and Epmeyer construct Z2 bundles over these K-theoretic spaces using differential operators. And for a compact spin manifold, they use the Dirac operator. So let me talk about these. These are another example of these Z2 graded H-principal Z2 bundles. And so for a principal bundle P, one associates to it a topological stack, which one should really think of as the equivalent of having an algebraic stack just in the world of topological spaces. And this is a quotient stack, BP, which is given by taking the space of all connections and acting on it with the gauge group. If Y is compact, then and spin, then one has this positive Dirac operator, and using this they define using this one defines this orientation Z2 bundle on BP, which at each connection or at each point in the space is given by the orientation of the real determinant line of this real differential operator. This should be not D, but rather a Dirac operator here. And taking unions, we get orientation on the entire moduli stack. Is the union of all isomorphism classes of B. Now there is a natural map from a classifying space, which is really just some topological, similar to this topological realization of Blanc, but for topological stacks here now. And there is a natural map from this into the K-theory space, which is a homotopy theoretic group completion, because this is an H space and this is a group like H space. So you kind of have a group completion here, which satisfies some weak universality property. And using this one, it extends this Z2 bundle to the entire K-theory space. In Cao-Gross-Joyce, the Z2 bundle is in fact proven to be strong H-principal Z2 bundle. And the grading that I give it is given by taking this Dirac operator Euler form of this K-theory classes alpha on each connected component of C, which is associated to the K-theory class alpha. And it is given, well, it's extended by group completion from the corresponding form on vector bundles, which is given in terms of an index of the Dirac operator of the adjoint bundle of P, where P is associated to E. So using these orientation bundles, which, as we saw, are now Z2 graded strong H-principal Z2 bundle, we can construct something that we will use to get our orientability on orientation on a differential geometric side for the non-compact setting. So to do that, let's take T be a tabular neighborhood of this strictly normal crossing divisor, which corresponds to a union of tabular neighborhoods of these irreducible components. And let K be the compact set, which corresponds to X without this tabular neighborhood. And choose some Y as a submanifold of X, which is a manifold with a boundary containing X. Then one can construct this double of it by gluing it to itself with an opposite orientation. And it is possible to show that this has a natural spin structure coming from the orientation on, coming from the spin structure on X, which is a natural one because it is Calabi-Yau. And we also use this, define this T tilde, which corresponds to union of this negatively oriented copy of Y together with closure of the tabular neighborhood. And for each pair of, so now we want to define kind of the moduli stack with a proper notion of orientability on this glued spin manifold. And to do that, we consider for any two principal UN bundles P and Q with an isomorphism which identifies them on T tilde, this space of connections, AP, AQ, together with the space of all isomorphisms between P and Q on T tilde. And then there is an obvious action of a gauge group on it, which acts on the connections the way that gauge transformations do, and by conjugation on this third term. Using this, we get again a topological stack, and we take union over all of the isomorphism classes of P and Q identified at T tilde, where then a projection from this triple to just the connections of P and of Q gives us natural maps from this newly constructed object to just these stacks of Joyce, Tanaka, Altmaier, which had orientation bundles on them. So we can define an orientation on this bigger thing by simply taking pullbacks of orientations here and their products. And this is all done in the sense of Z2 gradedness, so you have to keep track of that. And here the dual is important because if you don't take the dual, then you won't get isomorphism of strong H principal Z2 bundles, and then you won't be able to get the correct signs, and yeah, the isomorphisms won't extend. So let me just say how this actually relates to anything that I was doing, because right now I just kind of constructed this orientation on Y tilde, which is a completely different space that I don't really care about, but it gives me exactly what I want. So using this notation, Vy, meaning kind of the space of complex vector bundles, of continuous complex vector bundles, we have the fact that the stack on the previous page, constructed on the previous page, can be shown to be homotopy equivalent to this fiber product of these spaces of vector bundles. And one has a homotopy theoretic group completion from this space into the corresponding K-theoretic space, which extends the Z2 bundle like constructed on the previous page to the K-theoretic space. Now, we can define a map from this moduli space of bundles, or pairs identified at the divisor at infinity, into this space where we have orientation, mapping E, F, and isomorphism phi from E into F into the corresponding triple on the right side in the following way. So if we take E, so E tilde is given by gluing E to E along identity on the boundary, and then if we extend phi, which we had here, from the divisor to some small tabular neighborhood, then we can identify F with E, where E now is, we can glue F to E, where E is on the negative copy and F on the original copy, to get our vector bundle F tilde. And the F tilde isomorphism simply corresponds to identity on the negatively oriented copy and to phi in the original copy. So this is a well-defined map, and similarly, by group computation, one can extend this map to K-theory. And the pullback along this map defines, of these Z2 bundles that I just described on Y tilde, defines our Z2 bundles that we actually care about, living on these spaces of vector bundles or K-theory, identify like pairs of K-theory identified at infinity of X bar. So this is the DCO that appear in the theorem that you can prove is naturally isomorphic to the orientation on the product stack. So let me just, because I'm running out of time, say it quicker, a bit quicker now, how one can actually prove that this DCO that I obtained is isomorphic, or rather its pullback is isomorphic to this O theta bow tie. So for that, one considers this space of globally generated, vector bundles generated by global sections. And this story on K-theory and perfect complexes is reduced just to a story on vector bundles by using the fact that these maps are these vertical maps are homotopy theoretic group completions. So if you prove that the pullback of this gauge theoretic Z2 bundle to here is isomorphic to a pullback of our bundle O theta bow tie to here, then you will be able to prove that the pullback of a Z2 bundle here is isomorphic to a Z2 bundle here. And why this should be true, if we constructed our Z2 bundle on the right side, on the differential geometric side, using something living on this Y tilde, on this gluing, this comes from using something called excision principle. I kind of wrote down on this page what this does, but let me just say it. You take this product of orientations which live on the entire Y tilde, and you deform this pair of differential operators into something called a pseudo-differential operator, which lives inside of the original copy using the isomorphism phi, or phi tilde it was before, and where chi here is just some bump function which restricts your differential operator to live only in the original copy of Y. So if I go here, now we had this isomorphism here. We had the isomorphism here, and we removed the orientation information from here using this excision, such that all of the information now corresponds to taking a determinant of a pseudo-differential elliptic operator here. And that's all we care about, because solution to this operator, solutions to the operator acting on it and being equal to 0 all lie here. Right. So this explains why the differential geometric side makes sense. And on the algebraic geometric side, we had this problem that in this short exact sequence that we used, we were restricting to something compactly supported on D1, or on these divisors at infinity, which doesn't really fit into the differential geometric picture. So what you do is you take resolution of this compactly supported, of this codimension 1 supported thing by vector bundles, such that it is in some sense a common resolution, meaning that you have here given a resolution by E and then given a resolution by resolution factors through both of them. So the isomorphism that I wrote down before can be re-expressed using the using vector bundles and Dolbeault resolutions on it, and then using some rather complicated deformations. Well, using some complicated deformations of these complex determinant line bundles of Dolbeault operators of these vector bundles that I constructed here, one can express the orientation data on algebraic geometric side as having a real structure induced by Serre duality, which lives only on the original quasi-projective Calabi-Yau of some pseudo-differential elliptic operator expressed in terms of Dirac operators. So this is quite a tedious thing, and if you want to look it up, it's in my paper, but I do not recommend that. Yeah, so how much time do I have? 1 minute. So let me just say that using these isomorphisms, so we have these isomorphisms which come from the fact that our Z2 bundle are a strong H principal Z2 bundle, comparing the Z2 bundles under direct sums, and we can use these orientations. Sorry, we can use this isomorphism to compare our choices of orientations. So if we choose orientations on each connected component of the K theory, then we can compare these orientations using isomorphisms. And if we, if we do so, then first one needs to ask the question what happens when one interchanges the order of the K theory classes which classify the connected components of our moduli space or of our K theory space. And if we do so, we get this additional sign in front of the isomorphism under interchanging the order. And this introduces, so if we define epsilon alpha beta to be the signs comparing choices of orientation under these isomorphisms, which keep track of compatibility under direct sums, then these signs will satisfy this nice relation, which I wanted to talk about more, but these signs and satisfying such a relation are then used by Joyce to construct vertex algebras on moduli, on the homology of the moduli stacks that we were working with. And because this was now said all for the kind of differential geometric side, and we know that all of this pulls back to the algebraic geometric story, this can be said also for orientations O omega alpha, which are used to denote the pullbacks of these differential geometric orientations O CS alpha. So I have this summary here, but I won't repeat it because I'm already 1 minute over time, I think. So that is the end of my talk.